Okay, so today is it. Today's the last lecture. Um, so to tidy up what it is that we were talking about last time, couple of things. So one, we saw that after a little bit of discussion, there was a quantity that was actually left invariant by these Merbius transformations, and that quantity is the absolute value of the natural log of q over p, where we had points on the upper y-axis that were pi and qi. The distance between those points we defined in this way is the absolute value of log of q over p. And this was going to be our distance on the upper half plane. And so the way that we would do this is that if you wanted to compute the distance between 2 points, it was simple. The 2 points determine a non-Euclidean line in the upper half plane. You can take that line, so that line gives you actually 4 points. It gives you those 2 points and the endpoints of the non-Euclidean line, right? Which could be, one of those endpoints could be infinity. You then, by Merbius transformation, you map those points, or you map that line to the y-axis. Under that map, of course, the 2 points you pick in the upper half plane get mapped to 2 points on the y-axis, p and q. Whatever those 2 points are, you compute the distance, and this quantity is preserved by Merbius transformations, and so this is your distance that you can use on the entire upper half plane, and it's not affected by the Merbius transformation. So, and so you can use this, even though we've only defined this for points on the upper y-axis. You can actually use this for any 2 points in the upper half plane. Okay, so that is the nice thing about this. Okay, so that actually provides us with a notion of distance on the entire upper half plane. And as we saw last time, that if we look at the collection of points, so this box statement here, so consider the infinite collection of points 2 to the n I on the upper y-axis. So here's what a couple of them look like. Okay. So the distance between these points, the distance between 2 and 4i is log 2. The distance between 4i and 8i is log 2. The distance between 8i and 16i is also log 2. So even though it doesn't look like it, these are equally spaced points, okay, on the upper y-axis. Okay, so in terms of non-Euclidean distance, these are equally spaced points. Okay, so this led us to a notion of non-Euclidean distance that was strange in a couple of ways. So one, it was that there was this distance distortion near the boundary, right, where this was actually an accurate depiction, or rather, a depiction of figures of equal size. So these faces are of equal non-Euclidean size. So each smiley face you see here is the same size with respect to this non-Euclidean distance we defined. Okay. Another example is the following picture. So we're going to see another example of this later. You might recognize this as looking like an M.C. Escher picture, and in fact it is an M.C. Escher picture, or rather a mapping of an M.C. Escher picture. So the original M.C. Escher picture is called Circle Limit 1. So it says here, this is the half-plane version of Escher's Circle Limit 1. So if we take that Circle Limit 1 and we map it to the upper half plane, we can do this by this simple transformation that sends complex number z to 1 minus zi over z minus I. So mapping that transformation in this way, we have an upper half plane version of this, where these fish are actually the same size. Okay, so these fish are all congruent. All the white fish are congruent, all the black fish are congruent. These are all congruent, okay, in terms of non-Euclidean length. So every fish you see here is of equal size in the non-Euclidean sense. You see, as we get nearer the boundary, these fish look like they're smaller, but actually they're the same size, okay, as even these big fish out here, right? Okay, so again, that may seem a bit strange, and you may be skeptical about whether or not this provides you with a useful notion of length, but it does, right? So I mean, it actually satisfies all the things that we require or we expect the length to satisfy. The only thing is how it looks, right? Looks strange to us, but that alone is, of course, not a reason to discount anything. Okay. And so we've already seen the reflections of the upper half plane. And you might be confused because I've written reflections here in quotation marks. But remember that the reflections that we're calling reflections in the upper half plane, some are strange, right? In fact, the inversions, right, are strange. So some of the reflections are honest to God Euclidean reflections, right? So some are, Euclidean reflections. Across vertical lines, and some are inversions in unit circle. Right? Okay. And so if we knew how to invert in unit circle and we were able to horizontally translate, then we could actually reflect across a circle of any size, because we could also dilate, right? And so being able to invert in unit circle, being able to have Euclidean reflections, of course, we were doing this across vertical lines. These were the things that we were calling reflections, right? And the only reason we have to put these quotes here is because these inversions are not Euclidean reflections, but it's okay. Right, we call them, these are our reflections of the upper half plane, okay? All right, so that's what our reflections look like in the upper half plane. But question is, are there translations and rotations of the upper half plane? So the question is whether or not there exist isometries of the upper half plane that are analogs of translations and rotations in the Euclidean sense. Okay, and the answer is yes. Okay. So what are these going to be? They are going to arise in the same way that Euclidean translations and rotations arose. But how was that? Well, you might say translations and rotations kind of have obvious definitions. They were kind of naturally defined for us in the Euclidean sense because they were kind of obvious operations. But here, they're not. In the Euclidean sense, we had another way we could look at them, which was that both translations and rotations were or could be obtained by two reflections, a product of two reflections. And so we're going to view these in the exact same way. Yes, they are the transformations obtained as a product of two reflections. Of course, instead of being two Euclidean reflections, they're two non-Euclidean reflections. Okay. Now, there are two cases here, right? So the idea is that there are two cases. When the lines you reflect across intersect and when they don't. These two cases are going to give you whether or not what you're doing is a translation or a rotation. Okay, so when you are dealing with a product of two reflections, right, that means you have two lines you're reflecting across, okay, that are distinct. So in the upper half plane, those two lines could not intersect, or they could intersect, right? And so whether or not they intersect is going to tell you whether or not the thing you get is a translation or rotation. Okay, so let's see how this works. So a non-Euclidean translation is the product is the product of reflections in non-Euclidean lines that do not meet. So that do not meet and do not have a common end. Okay. Now, we have to include the do not have a common end thing because we don't want them like meeting at infinity. So if you have a product of reflections in non-Euclidean lines that do not meet and do not have a common end, this is going to be the notion of a translation. Okay, so an example is the map Z to 2Z. Okay, this is a product of reflections. So this is a product of reflections in the circles with center 0 and radius 1 and root 2. Well, I should say radii here. It kind of sounds awkward otherwise. Okay. What does this thing do? Right. So, the mapping Z to 2Z, this is obtained by reflecting across the non-Euclidean line that has that semicircle centered at 0 with radius 1, and then reflecting across non-Euclidean line that is semicircle with center 0 and radius root 2. Okay, so that those two reflections in those circles yield this this map. What does this do? What does this map do? Before we look at anything, what should it do? If this is going to properly be a translation, right? If it's going to be an analog of a translation, then should it change the size of the figure? Well, no, right? Because Euclidean translations didn't change the size. And so these things we're calling translations shouldn't change the size. Of course, that is going to be relative to what our notion of size is, right? So in the Euclidean sense, a translation didn't change the size of a figure, right? If you translate a smiley face, we'll say, in the Euclidean plane, the size of that smiley face in the Euclidean sense didn't change. So the same thing is going to be true for us, but of course the apparent size is going to change. And the reason why I brought up smiley faces, what does this map do? Looking at this familiar diagram that we had before, this map takes each of these smiley faces and sends it to the one above. So this smiley face gets mapped to the smiley face above here, and this smiley face that I'm pointing to gets mapped to the top smiley face here. Okay, so this is a translated copy of the smiley face below it. That's true for all of these. Okay. And so, of course, to our eyes, it looks like this smiley face is bigger, right? But it's not. We know that these are all smiley faces of equal non-Euclidean size. So this translation is not actually altering the size when it maps, say, this smiley face to the one above it. Okay. All right. What is... So first of all, when you typically have a reflection, what's one of the things that characterizes a reflection? Well, a reflection is a type of transformation. Like if I asked you to figure out what some given transformation was, and I only gave you maybe some of the points, right? So go back to chapter 3 and think about how many points you needed to determine what an isometry was exactly. But one of the things that characterized an isometry, or a reflection specifically, was that a reflection fixed a line, and that line that it fixed was the line of reflection. So that's a reflection, right? So then the question is, what about a translation, right? So a translation, if you were translating, say, a line in the direction of the line, then it would fix that entire line. But otherwise, right, a translation moved things. So the question is, what does the translation do in the upper half plane? Well, in the upper half plane, translations have what's called a translation axis, which is a unique line that is fixed by this translation. But it's not the only line that's fixed by the translation. Okay, so this translation, so there is a unique line. So this is a non-Euclidean line. I'm going to write the whole thing. So it's a non-Euclidean line that is fixed. See, I make it sound like this is the only line that's fixed when I say unique line, but that's not what I mean here. I just mean that there is a line called the translation axis that is unique, that is fixed by this thing, but it's not the only line that's actually fixed. Okay, so I'm going to get rid of unique here, even though the translation axis is unique, but there's more than just that line that's fixed. Actually, let me think about it for a second. Actually, no, this is the unique line. Okay, here, this is better. So there's a unique line that's non-Euclidean that is fixed by these translations called the translation axis. So what I had written was fine. But also, there are curves that are constant non-Euclidean distance from the translation axis. That are also fixed. And these are not non-Euclidean lines. Okay. Okay. So to see what this picture looks like, going to show you these two pictures. Now, what are these two pictures showing you? Well, in this picture, this is what happens when my translation axis is vertical. So we'll take my translation axis being this line here, the y-axis. Okay? So what are these light gray lines coming in at a V? These are my not non-Euclidean lines, right? Notice that these lines that I've drawn in are not non-Euclidean lines. They're not lines in the upper half plane. Okay? But they are lines that are equal non-Euclidean distance from my translation axis, and they are also mapped onto each other. So they're mapped onto themselves by this translation. What does this translation do? It sends every non-Euclidean line here, in this case it's intersecting it perpendicularly to this translation axis, sends every single one of these to the one above it. So this semicircle gets sent to this one, this semicircle gets sent to the one above it, this semicircle would get sent to this one up here that has this arc. That's how this translation is working. And it maps these light gray lines onto themselves, it maps the translation axis onto itself. Okay, so that is what happens when your translation axis is a vertical line. The other case is, what if your translation axis is the other type of non-Euclidean line? So let's say your translation axis is this thing. Okay, it's this semicircle. In that case, if this is your translation axis, the equidistant curves that are, some distance r, we'll say, on either side of this translation axis are these other non-Euclidean lines in light gray here. Okay. And so some other examples of non-Euclidean lines here are here on this side, here's one, and here's others on this side. What does a translation do if your translation axis looks like this? It sends each of these things to the next one. Okay, so let's just go through it here. It would send this line to this one. And it would send this non-Euclidean line to this vertical line. And then it would send this vertical line to this non-Euclidean line. And it would send this non-Euclidean line to this thing. And it would map the translation axis onto itself. And these two light gray curves would also be mapped onto themselves, even though they're not non-Euclidean lines. Okay? So think about this moving like this. That's how this is going. So this gets sent to the vertical line gets sent to this, and this, and this, and this, and so on. Okay, and so these translations can look weird, right, in the upper half plane, which is something that you can kind of expect. Okay. Let's see what rotations look like. So a rotation this is the non-Euclidean analog. So what does a rotation look like? This is a product of reflections in two non-Euclidean lines that meet at a point P. Okay, this is rotation about P. Okay. So, how does this behave? Well, it fixes P. Okay. And points at non-Euclidean distance R remain at non-Euclidean distance R. All right, thus, these points move around a non-Euclidean circle of radius R. Now there's an aside to be noted here. What does a non-Euclidean circle look like? Well, we can actually define a non-Euclidean circle using this operation of rotation, but I'm going to actually draw the picture clean, and then I'm going to show you the picture of the rotation. In this case, what does a non-Euclidean circle look like? Well, if I have my upper half plane, so pretend the paper's upper half plane. What's a non-Euclidean circle look like, right? Lines are not the same as Euclidean lines, but a non-Euclidean circle looks like a Euclidean circle. Okay, but a Euclidean circle has its center right here. A non-Euclidean circle has its center like here. So non-Euclidean circles actually look like Euclidean circles, but their center is not where the Euclidean center is. So a non-Euclidean circle, so it looks like a Euclidean circle, but its center is lower. Right? Now that makes sense, of course, if you think about it, right? Because if we're thinking about what this distance is, if this is R, well then that apparent distance cannot look the same above, because we know up here the computation is different. So then this distance is also R, right? You can draw pictures of this if you like using one of those examples like we did of equally spaced points 2 and I on the upper y-axis. Okay, and so as an example, not of a non-Euclidean circle, but of rotation, take the product of reflections that is z getting sent to minus z bar and z getting sent to minus 1 over z bar. Right? These are my two basic reflections. So what is the result? The result is rotation. So rotation through an angle pi about I. Why? Well, this is a reflection across the y-axis. And this is a reflection across unit circle. All right, so the upper unit semicircle intersects the y-axis at the point 0, 1, which is, of course, the complex number I. Okay, so that's their point of intersection. So that's why the resulting thing. Now, why is it pi? It turns out that if you have two non-Euclidean lines through P meeting at angle theta, then the product of reflections in these lines is a rotation about P through angle 2 theta. Okay, and so these two lines, of course, meet at pi over 2, but if you do the product of the reflection, you get twice that, which is 2 times pi over 2, or pi. Okay, so that's where the pi comes in. Now, what does this look like? So rotating about I looks like this. In gray, I have the two non-Euclidean circles. I have an example of two non-Euclidean circles with center I. So I is the center of both of these circles. Okay. So this point I is the center of both of these light gray circles here. So you see the center is lower than it should be if they were Euclidean circles. Okay. And so, what does it mean to rotate here? Well, if I were to rotate, say, pi over 4 about I from this picture, it would rotate each of these non-Euclidean lines to the next one. Okay. So I have this broken up into angles. If I rotated, say, by pi over 4, it would rotate each of these non-Euclidean lines to the next one. So I have 4 non-Euclidean lines here, right? 1, 2, 3, 4. Okay. Right, and so each of them would rotate to the next one. So that's why, again, just looking at it, you wouldn't necessarily view these lines as being rotated versions of each other, but they are. Okay, and this is the diagram that explains why that's the case. Okay. All right. Okay. So there is a limiting case. So limiting case for rotations. So the limiting case for rotations is when the point P is on the boundary. So when P is on the boundary or at infinity, right? So this is called a limit rotation. And in this case, everything that gets mapped onto itself is called a Horus cycle. So, and each curve fixed by this is called a Horus cycle. So there are some really cool pictures that you can generate of Horus cycles using software. So if you Google Horus cycle, you'll see a bunch of good pictures of this stuff. Okay. All right. So this is there's an easy example of this. So I'll just give the example. If you look at what is the horizontal translation that sends z to z plus 1. This is a product of reflections. So this is a product of reflections in vertical lines x equals 0 and x equals 1 over 2. X equals 1/2. Okay. All right. So you might think that this is actually a translation, but it's not. It's a rotation. And the reason it's a rotation is because they have a common end. Their common end is infinity, right? They go off to infinity. They don't have a common endpoint on the x-axis, but they have common ends on at infinity. Okay. And ultimately, this is what the picture looks like for these limit rotations. Okay. So in these cases, my vertical lines here are the translated versions of each other. These light gray lines are these limit circles or Horus cycles in this case. Another example is in this example here. This is the more typical case. So this is a really special case. This is not what it typically looks like. So this is kind of like the most degenerate case here. If you want to see what it typically looks like, if you look at the reflection that sends z to z over 1 minus z, what you get is this picture. So each of these non-Euclidean lines here are translated copies of each other. Okay, and these gray circles that are tangential to the boundary at 0, these are the Horus cycles. Notice these circles that are tangent to my boundary, these are not non-Euclidean lines, right? Because they're not semicircles centered on the boundary, they are circles tangent to the boundary. Right, those are the Horus cycles in that case. Okay. So that's pretty much all I wanted to say. One more thing that kind of ties this in the last section, the very last section of the textbook, there's a proof of one last fact, which is the 3 reflections theorem for Merbius transformations. So 3 reflections theorem for the upper half plane, just to kind of tie this back to what we did before and show how similar this is to Euclidean geometry, much more so than spherical geometry is. So the 3 reflections theorem for the upper half plane states that any Merbius transformation is a product, so any Merbius transformation of the half plane, I should say. So any Merbius transformation of the half plane is a product of at most 3 reflections. Okay, so just like the isometries of the Euclidean plane were a product of at most 3 reflections, this is also true for the isometries of the upper half plane, which are Merbius transformations. Okay, and that is it. Okay, so that's everything I wanted to say from this material. Now, the last couple of things to kind of tidy up everything that we've said so far in the course is the following kind of overall review. So, where were there hints of some of this stuff? So it turns out that there were earlier hints of non-Euclidean geometry, and I mean there have been even since the ancient days. So the most the most obvious way of saying that even the ancients knew that something was up with the parallel postulate was that Euclid went out of his way to not use it like as much as possible. So in fact, he barely uses it at all. And if you go through Euclid's Elements, I think like the first time he uses it is after he's already proved like 30-something things using the other postulates. So it was used very sparingly. I believe most ancient mathematicians that thought about it probably thought that it could be proved from the other postulates, but couldn't figure out how to do it. And of course, now we know the reason they couldn't figure out how to do it is because it's impossible to do it, because hyperbolic geometry, the upper half plane, is an example of a space that actually satisfies all of Hilbert's axioms except the parallel postulate. Okay. So uniquely, the parallel postulate is the thing that fails. This is the closest you can literally build a geometry that is exactly like Euclidean geometry except for the parallel postulate, and you still get a coherent geometry in every other way. Okay. So this was done by Janis Bolyai and Nikolai Lobachevsky independently. In the 1840s. Okay, so you can have a look at their life's work. I think it was Bolyai. Originally, this was published in like an appendix to some math textbook that his father had published. So even though this was done in like the 1840s, there were earlier hints of what was going on. So Gauss, which you've no doubt heard of, Gauss actually had probably more or less figured this out, but was essentially afraid of too much ridicule, or maybe it not being worth it for whatever reason. Gauss had a lot of idiosyncrasies when it came to, like, he was kind of a perfectionist, and he had this thing of he wanted all of his results to kind of appear like they came out of nothing, and he didn't want to necessarily have an entire paper trail of all of his thoughts, and so he was really very guarded about his publishing methods, more or less, and on account of it, for whatever reason, he didn't publish this. But Gauss had been working on the notion of geometry of surfaces in space. Okay, and when you work on the geometry of surfaces, you come to realize that there's a lot to be said about non-Euclidean things on surfaces. Because on surfaces, as we've seen with spherical geometry, when you start to talk about things like a shortest path between 2 points, what you end up with are things that are not Euclidean lines, but they behave like them geometrically. Okay, so this leads you to the idea of geodesics. Right, so geodesics are the shortest paths, okay, in whatever surface you're dealing with. Now, there's a lot to be said there, because there's a whole, unfortunately, this is something that requires a ridiculous amount of background to get into. So the geometry of surfaces and the geometry of curves, both in space and in the plane, and surfaces in space, this is something that is done in Math 436. So 436 is the study of the geometry of curves and surfaces. If you don't see it in a course like that, then unfortunately the way that it works is if you go to grad school and you take your first course in like serious geometry in grad school, you're going to start out not in dimension 2 or 3. You're going to start out immediately, or maybe I should say dimension 1 or 2. You're not going to start out in dimension 1 or 2. You're going to start out immediately in general in dimension. And rather than talking about curves and surfaces, you're going to talk about general manifolds or Riemannian manifolds. And it's fine to do it that way. That's the way actually I did it. But if you do it that way, then you kind of miss out on how it was built up, and maybe you lose a little bit of intuition for how these things went. So anyway, Gauss proved many things about surfaces. So one, of course, there was the notion of curvature, okay, of a surface. And in fact, it was this curvature and considering surfaces of constant curvature that would end up being so important. These spaces with constant curvature would be called model spaces for our non-Euclidean examples. So constant curvature yields model spaces for our non-Euclidean examples. So, for example, there is a surface of constant curvature -1 called the tractroid. And this surface is strange because it is generated from a curve called the tractrix. Here's the tractroid, and here's the tractrix curve that generates it as a surface of revolution. Okay. So it turns out, what is this thing? This thing provides a nice model for hyperbolic geometry, just like the upper half plane. Okay. Now, Gauss also showed something called the Theorem Agregium, which is something that you will do if you take Math 436. This is the remarkable theorem. And what this essentially, the most important thing that this allows you to do is, as I previously mentioned with the sphere, the reason why spherical geometry was not considered to be opposed to Euclidean geometry was that everyone that worked on it viewed it as sitting inside of R3, right? Sitting inside of Euclidean space. And so on account of that, they kind of viewed spherical geometry as just this weird thing that sat inside Euclidean space, and so somehow it was like inherently Euclidean, even though the geometry of it, of course, was definitely not. But the remarkable theorem says that it doesn't actually matter how the thing sits inside Euclidean space. And that can be made precise with a statement of it, but I'm not going to go into that. But basically, the remarkable theorem says that actually we can toss out the ambient Euclidean space that it sits in. And if we do that, we can actually just consider the inherent or intrinsic geometry of the surface itself, that is the sphere itself, and we don't need to make any reference to the Euclidean space it sits inside. And so when you come to it, the only universe you know exists is the sphere itself. There is no outside space. And all the geometry that we do like that, ignoring the ambient space, is the same as the geometry we'd be doing if we actually paid attention to the ambient space. And so in that way, spherical geometry is its own thing. It's not Euclidean geometry because I don't even need it to sit inside of a space. Okay, is the point. All right. And so this all leads to these examples like the tractroid and like various other. So here's an example of projecting the sphere or preserving the geodesics on the tractroid to plane. This can be done in a way that sends the geodesics that we talked about to Euclidean straight lines in the plane, in the projection. Okay, an example of this is this earlier transformation we talked about. So remember that upper half plane version of this? This is another model for the upper half plane called the conformal disk model. This was invented by Beltrami. Okay, so to kind of go through that really quickly and give you an idea. So Gauss basically had everything that was needed to figure out what was going on here. And Gauss had a student by the name of Riemann that did most of the legwork in kind of establishing everything that was needed as the foundation for what would ultimately be called Riemannian geometry. Okay. Now, Riemann did not himself come up with everything that is now called Riemannian geometry, but it's named after him because it was directly from... So Riemann was kind of a sickly guy. He ended up, I believe it was tuberculosis, and he thought that a change of climate would help him because Riemann was German. And so he moved to Italy, which had a nicer climate than Germany. But it wasn't enough. He ended up dying in Italy, but not before he had kind of established a little circle of mathematicians around himself in Italy. And it was those Italian mathematicians that kind of carried on his work. And so that's why you will see, if you study geometry more and more, that at that turning point, all of the names in geometry that are very important were all Italian. And so one of the biggest contributors after this was Beltrami. So Beltrami, you will hear a lot of names over and over again. Levi-Civita is one. Beltrami, Codazzi. There's a ton of Italian mathematicians, Italian geometers that were huge and have a ton of stuff named after them. And this is because they were in Riemann's inner circle or influenced by it. And so Beltrami came up with the conformal disk model of hyperbolic space, or of the hyperbolic plane. Or I should say the conformal disk model of hyperbolic geometry. Here's an example of what's going on there. So the boundary is now not the x-axis, it is this circle. Okay, and all of these fish, again, are the same size. Okay. All right, so rather than get into the specifics of the conformal disk model, I'll say the most important thing. So one, all of these models of hyperbolic geometry are isomorphic. And they're all isomorphic to the upper half plane model. So we use the upper half plane model, and that's perfectly fine because all these other models that we could have used, like the conformal disk model, which would have taken a lot more effort for us to develop, it's actually the same as the upper half plane model. So the upper half plane model is actually kind of our best, most efficient example of this model space. Okay. So a couple of last things, where this is headed. If you're interested in the direction that this is going in, where this is headed is, I already mentioned, geometry of curves and surfaces in space is the first thing to think about. That sort of geometry leads directly to what is called Riemannian geometry. Riemannian geometry is a study, or is the study of objects that are called Riemannian manifolds. Now, I'm not going to go into exactly what it is, but a manifold is essentially a space that locally is Euclidean. So locally it looks flat. Right? It has curvature 0, okay, in the Gaussian sense. But this is locally. It is locally it looks like Euclidean geometry, but globally it's very much not. Now what I said, this is a little imprecise and not totally correct, but this is the idea. And Riemannian refers to an extra structure on top of that, which is what's called a Riemannian metric. Which is essentially a way to compute distances, okay, on this space. Okay, and the distance that you get out of it might not always be exactly like the distance that you're used to in Euclidean sense. And so the most important thing to note here is that all types of geometry we've seen are special cases of Riemannian geometry. So both Euclidean geometry and hyperbolic geometry that we've seen are just special cases of Riemannian geometry. Okay, the spherical geometry as well is a special case of Riemannian geometry. Okay, and so all these things sit inside it. Affine geometry. Affine geometry and projective geometry, I'd have to say a little bit more to really fit those in. But basically think of Euclidean geometry, spherical geometry, hyperbolic geometry. So that's what I'll write out here. These are all examples of Riemannian geometry. Okay. All right, so that is the course. Now, as mentioned in the announcement, I will be holding office hours tomorrow from like 3 to 4. So any additional questions you might have, any remaining questions, feel free to stop by and ask. So I'll be there, and and I'll be there until there's no one there. So if you come and there's only like a few, 10 minutes left, I'll stay until I've answered all the questions anyway. So anyway, I will see you all tomorrow, and pay attention to announcements when I'll post the final exam in a couple days and all that.